Huawei is very dangerous.
Rarely does a country go to war with a private company.
We have met the enemy, and it is Huawei.
We're not going to do business with Huawei.
Huawei represents a national security risk.
But is this really about Huawei, or is it something bigger than that?
In a confidential facility located in Dongguan, China, something is happening that was recently considered impossible. Huawei, the company that many believed was finished after American sanctions, has successfully tested its own extreme ultraviolet lithography machine. They've manufactured the most complex technological device that exists, a machine that until now only one company worldwide had been capable of producing, and they're using it to manufacture 3-nanometer chips. The same specialists who claim China would need 15 years to reach this point now watch as their forecasts collapse in real time. To understand why this is so extraordinary, you need to understand what an EUV machine really is. This isn't common industrial equipment. Each one costs more than $350 million, surpassing the price of a Boeing Dreamliner and requiring around 40 containers for transport. Inside, light is used with an exact wavelength of 13.5 nanometers to etch circuits on silicon wafers that are 30,000 times thinner than a human hair. For decades, only ASML, a Dutch company, was able to manufacture these machines. Their monopoly was absolute. When the United States government pressured the Netherlands to stop selling this equipment to China in 2019, it was assumed that the Chinese dream of producing advanced semiconductors had reached its end. The Trump administration imposed sanctions on Huawei, cutting off its access to American technology and advanced tools for chip manufacturing. ASML, under political pressure, stopped sending EUV machines to China. SMIC, Huawei's main manufacturing partner, was limited to DUV technology, which only allows reaching down to 7 nanometers. At first glance, the sanctions seemed to be a complete success. Chinese access to the most advanced technology was blocked. Analysts, experts in semiconductors, and policymakers agreed that it was the end of Chinese aspirations in this field. But China did not give up. It entered what many describe as a mode of total mobilization. Thousands of millions of dollars were deployed to research and development. Xi Jinping raised semiconductor self-sufficiency to a national security priority at the same level as food or energy security. Universities, private companies, and state-owned enterprises began to work in a coordinated manner in a massive effort to achieve technological independence. In 2025, the results of that strategy are visible. Huawei did not simply try to copy ASML's approach. They developed a completely different technology known as laser-induced discharge plasma, or LDP. While ASML uses plasma generated by lasers impacting tin droplets with high-powered CO2 lasers, Huawei's system vaporizes the tin between electrodes and subjects it to high-voltage electrical discharges. This process generates plasma, which emits exactly the same extreme ultraviolet wavelength necessary for chip manufacturing, but through a fundamentally different mechanism. The system is more compact, simpler, and potentially much cheaper than the enormous Western machines. This LDP-based EUV system is currently in the testing phase at Huawei's plant in Dongguan. A Chinese company identified as a possible national leader in lithography recorded a patent for this technology in 2023, and now that idea is becoming reality. Trial production is planned for the third quarter of 2025, and mass production is targeting 2026. If the project is successful, China could flood the market with domestic chips of 3 nanometers, completely breaking the sanctions wall that supposedly had to contain them for a decade. This doesn't only involve Huawei, SMIC is also actively involved. Together, these companies not only seek to catch up with the West, but to surpass it. Reports from the South China Morning Post point out that a team from Huawei achieved a key advance in EUV light sources, reaching the critical 13.5 nanometer wavelength again. At the same time, the Institute of Optics and Fine Mechanics from Shanghai, led by researcher Lin Nan, developed an extreme ultraviolet light platform with power and operational stability considered competitive at the international level. Multiple research teams across the country have achieved simultaneous advances in light sources, optics, and lithography systems, which reveals a nationally coordinated strategy and not just isolated efforts. The importance of 3 nanometers is enormous. Smaller chips imply an exponential leap in power with lower energy consumption. A 3-nanometer chip can integrate almost twice as many transistors as one with 7 nanometers, increasing performance drastically and reducing energy consumption up to 30%. This would allow advanced artificial intelligence models to run directly on phones, enable real autonomous driving, and accelerate development of quantum computing. Western leadership in this technology sustained the dominance of companies like NVIDIA and Apple for years. If China manages to produce these chips domestically, it not only enters the game, it can completely redefine the rules. The signs of progress were already visible. In 2023, Huawei launched phones with 7-nanometer chips, despite the sanctions, manufactured by SMIC using DUV techniques. In February 2025, the founder of Huawei informed Xi Jinping directly that the chip shortage was decreasing, which reflected growing confidence in national production. Moreover, NVIDIA began to warn their investors about Huawei's advances in artificial intelligence chips. When the global sector leader publicly acknowledges a Chinese competitor, the threat is real. The market value of NVIDIA fell by $127 billion in a single day after the announcement of Huawei's 91010B chip, which supposedly matches the performance of the H100. In December 2024, the ASML executive director stated that China was between 10 and 15 years behind without access to EUV. That margin is being reduced at an unexpected speed. Significant challenges remain. China is still lagging behind in manufacturing scale. The ASML ecosystem took 20 years to perfect. Huawei's LDP technology is promising, but it still needs to prove its commercial viability. Current yield rates are estimated to be between 20 and 30%, very below the 70% commercial threshold, and far from the more than 90% achieved by ASML machines. Problems in the testing phase could delay mass production, and the transition from laboratory to reliable manufacturing remains complex. Meanwhile, a team from Peking University published a paper in Nature Electronics that left Silicon Valley engineers astonished. They built an analog computing chip based on resistive memory that performs calculations 1,000 times faster than NVIDIA's GPU H100 and consumes 100 times less energy. They made it using 7-nanometer technology, never sanctioned because it was considered obsolete. Jensen Huang, NVIDIA's CEO, anticipated this at the Artificial Intelligence Summit from the Financial Times in London, where he asserted that China will win the AI race. When someone who built a billion-dollar empire declares that his own technology is approaching obsolescence, analog computing, abandoned due to accuracy problems, has resurfaced thanks to a key advance: resistive memory cells that store multiple levels of resistance. In these chips, memory becomes the processor, allowing thousands of simultaneous calculations in the same physical space. The Chinese team achieved an improvement of 5 orders of magnitude in analog precision, achieving accuracy equivalent to 24-bit digital systems. This advance is not theoretical. It was manufactured using commercial processes existing in Chinese factories. United States sanctions designed to hinder progress ended up driving innovation. Huawei is the clearest example. Far from collapse, they developed their own operating system, their own chips, and expanded their global presence. Now the pattern repeats on a larger scale. While the West was perfecting increasingly powerful and energy-expensive digital GPUs, China questioned whether it was necessary to continue using digital chips. The real battle is one of energy. An analog chip that consumes 7 watts compared to the 700 watts of a GPU changes the rules completely. China also offers electricity subsidies and builds infrastructure designed for high-performance computing. The combination of ultra-efficient chips and cheap energy isn't an incremental improvement, but a paradigm shift. The applications are obvious: 6G networks, artificial intelligence trained in days instead of months, phones with local AI, more autonomous drones, and more efficient military systems. Today, Silicon Valley lacks a clear answer. NVIDIA continues to invest in digital GPUs. Intel faces advanced manufacturing issues, and AMD tries to catch up with competitors. Meanwhile, China is already working on the next generation of analog chips with larger arrays, better calibration, and expanded capabilities, marking a profound shift in the future of global computing. Beyond the immediate impact on the semiconductor industry, this advance modifies the way states plan their technological sovereignty. For decades, competitive advantage was measured by who designed the smallest chips or who controlled the key patents. Now the focus shifts to the ability to integrate research, manufacturing, energy, and infrastructure in a coherent strategy. China demonstrates that coordination between industrial policy, public financing, and scientific objectives can accelerate processes that in other countries depend on fragmented markets and long investment cycles. For years, confidence was based on the idea that certain technological barriers were practically insurmountable. EUV lithography and high-performance computing functioned as natural walls. The emergence of alternative solutions breaks that assumption and forces a rethinking of risk models, stock market valuations, and long-term strategies. Innovation no longer advances solely through incremental optimization, but through conceptual leaps that may arise outside traditional poles. The relationship between software and hardware also changes. With more efficient and specialized chips, algorithm design begins to adapt to non-digital architectures, which opens a completely new field for artificial intelligence. Models trained to leverage analog computing can solve specific problems with lower energy consumption and greater speed, disrupting the economics of data centers and reducing dependence on massive infrastructures. This has direct implications for countries with energy constraints that could access advanced capabilities without requiring enormous investments. On the geopolitical level, technological fragmentation is accelerating. Instead of an integrated global chain, parallel ecosystems emerge with their own standards, providers, and platforms. This bifurcation reduces interdependence, but also increases transition and adaptation costs. Multinational companies are forced to decide in which block to operate, what technologies to adopt, and how to manage increasing regulatory risks. Technological neutrality becomes increasingly difficult to sustain. Talent development takes on a central role. It's not only about electronics engineers, but specialists in advanced materials, plasma physics, hybrid system design, and unconventional computing architecture. Countries that fail to attract and train these profiles quickly run the risk of being left behind, even if they have financial capital. Deep and applied knowledge becomes the true bottleneck of industrial development. From an economic point of view, the drastic reduction in energy consumption in computing can redefine entire sectors. Computationally intensive industries such as biotechnology, climate simulation, or advanced engineering could expand to a scale previously unfeasible. This not only boosts productivity, but alters the global distribution of comparative advantages. Regions that previously lacked infrastructure for large data centers could become competitive with more efficient technologies. The Chinese case shows that technological sanctions have non-linear effects. Instead of halting progress, they can redirect it toward unexpected solutions. When a door closes, alternative paths are explored that with time become even more disruptive than the original technology. This phenomenon forces us to rethink the use of restrictions as a strategic tool, since their long-term consequences can strengthen precisely those one attempts to weaken. This process is also redefining the notion of early advantage in technology. For years, coming first meant dominating for decades because the entry costs and technical complexity acted as almost insurmountable barriers. However, when a lagging actor adopts a different approach and jumps directly to an alternative architecture, the pioneer's advantage can be diluted quickly. Instead of following the same path step by step, entire stages of technological development are shortened. leaving obsolete assumptions that seemed immovable. If computing stops being a voracious consumer of electricity, the calculations on installed capacity, transmission networks, and storage change radically. Countries facing physical limits to expand data centers can rethink their digital strategy. Computational efficiency becomes a public policy variable as important as electricity generation capacity or access to fuels. By reducing dependence on external suppliers, local businesses gain predictability and can invest with longer horizons. This stimulates the appearance of complete value chains within the same country or economic bloc, from basic research to the final product. Over time, this integration tends to generate economies of scale that further strengthen technological autonomy. Not all countries have the institutional capacity to coordinate universities, companies, and state agencies in long-term projects. Those who depend exclusively on the private sector may remain at a disadvantage compared to models where the state assumes an active role in strategic orientation. This doesn't imply the disappearance of private innovation, but its alignment with broader national objectives. Systems of surveillance, data analysis, and real-time decision-making benefit enormously from more efficient and compact architectures. Smaller equipment with lower energy consumption can be deployed in remote or mobile environments, expanding operational capabilities without increasing necessary logistics. This change alters the traditional balance between size, technological power, and reach. Investment funds and large institutions are increasingly evaluating the risk of being exposed to technologies that could lose relevance. The expectation that alternative standards will arise drives diversification into markets and companies that were previously considered secondary. This capital reassignment can further accelerate the consolidation of new innovation pools. The success of non-conventional approaches legitimizes exploration of ideas that for years were discarded for not fitting into the mainstream. Analog computing, for example, goes from being an academic niche to a field with real industrial applications. This change in mindset can open the door to further technological disruptions difficult to anticipate. Traditional educational programs focused almost exclusively on digital paradigms run the risk of becoming outdated. Universities and training centers must adapt curricula to incorporate new disciplines and hybrid approaches. Those institutions that react quickly will not only form more competitive professionals, but will also become key nodes of the next wave of innovation. The possibility of executing advanced artificial intelligence locally without depending on large centralized platforms has profound implications. It improves privacy, reduces latency, and democratizes access to sophisticated tools. This could decrease power concentration in the hands of a few corporations and allow small companies or even individuals to develop advanced solutions with limited resources. The technological leadership of the future will not be defined by a single progress, but by the ability to adapt quickly to structural changes. Flexibility, resilience, and strategic vision become as important as innovation itself. In this new context, those who manage to anticipate transitions and act before they become obvious will set the pace for the next stage of global technological development. What does this mean for the future of technology? Are we witnessing the beginning of a new computing era where energy efficiency matters more than raw power? If you want to stay ahead of these developments and understand how technology is reshaping our world, subscribe to our channel and join the conversation in the comments below.